I want to welcome you all to our 4th annual Asteroid Day event here at the National Atomic Testing Museum. Across the United States and the world today, of course in some places this day is already over, but there are events taking place to raise awareness of the potential threat that asteroids pose to the planet. And Ben is actually going to talk a little bit more about Asteroid Day itself and where it came from and why it's important when he gets up here. But I just wanted to let you all know that we're so thrilled that you're here. This is the only Asteroid Day event taking place in the state of Nevada. So we are thrilled to be the ones hosting it, and we're glad you're all here for it. I'm going to tell you a little bit about our speaker before I turn over the mic to him. He is a multidisciplinary scientist with professional experience in geology and geophysics. Hold on, my lighting got bad. Space science, health physics, and hydrology. He's been a frequent host and subject matter expert on a variety of programs on Nat Geo Channel, Travel Channel, Weather Channel, and History Channel, so some of you may be familiar with him already. And he currently works as a senior scientist for MSTS, which is the contractor at the Nevada National Security Site. He has a bachelor's in geology from the University of Wyoming and a master's in space studies from the University of North Dakota. Please join me in welcoming Ben McGee.
Can everybody hear me? Thank you very much. First, I want to thank the National Atomic Testing Museum for having me, for hosting Asteroid Day. I've been a champion of this since it started, and I'm particularly excited. I mean that you all turned out. I mean this is the best Asteroid Day turnout that I've ever seen here, and also because this is an update to a talk that I gave for Asteroid Day 2 years ago, and 6 people saw it because it was monsoon season. There was a lightning storm, and so I politely gave it. I basically sat down next to everyone, and we all watched the presentation together. So anyway, thank you very much, and I'll try and move around because I know the positioning here. I'm going to be blocking somebody. So Jordan already introduced me. Yes, basically I get myself into trouble wherever I go. It's what I've gotten good at. And why am I giving an Asteroid Day talk? One of the things I did, I worked at Bigelow Aerospace, which is a local aerospace firm here in the Valley. And we've got a module on the International Space Station. They do inflatable spacecraft. And I was their radiation guy. But it also had to do with the space environment. And yeah, I got myself into a bit of TV trouble, which is a complete accident, and that's a different story. But yeah, you might see me pop up every now and again to talk about things exploding and asteroids and supervolcanoes and things like that. And I work out at the Nevada Test Site, and this talk is all about how the two meet. So how can asteroids and the test site, how do they relate? And actually, the connective tissue is really deep. But first, we'll start with Asteroid Day. What is it? What is Asteroid Day? Well, in the promotional literature, Asteroid Day is an awareness movement that asteroids are out there and they could hit us, and that we should be thinking about, doing something about it. It's now International Asteroid Day, so last year the volume got turned up a little more, and things are happening all over the world. And really, I think Larry Niven, who's a sci-fi author, summed it up perfectly. Why Asteroid Day? Well, it's because the dinosaurs went extinct because they didn't have a space program. And if we don't have a space program too, we'll go extinct and it'll serve us right. That, in a nutshell, is how I see Asteroid Day. So why June 30th? And this is where we start diving into history. So June 30th, this day is not an accident. Asteroid Day is today because it is the anniversary of the 1908 blast in Siberia in an area called Tunguska. Possibly a comet, possibly an asteroid. It blew up in the atmosphere with such force, it's about a 10 to 15 megaton blast. So that's equivalent to the largest U.S. nuclear test, Castle Bravo. And so that's kind of a sobering data point. What happened? Well, this object came from space over largely unpopulated Siberia, fortunately, and it knocked down 80 million trees. I mean, it flattened huge swaths of forest. And we don't have a picture of that, but we do have a picture of the trees. That's it. This used to be forest. This is not grass in a field. This is actually hardwood. And it's all just laid over for, hundreds of miles. So that at least anchored that this can happen in history. So now I've got to explain, what is an asteroid? You hear the term talked about. But if you'll indulge me for just a little bit, these things are way more interesting than I think they're given credit for. People draw them like potatoes in space. And you watch Star Wars and they all look the same. And they're actually a bunch of little details. They're material, they're little bits left over, relics of the early solar system. And what do I mean by that? Well, these are actual pictures of things that we've visited with spacecraft. They go from the really small to, actually, 4 Vesta here is pretty decent sized, and we're orbiting spacecraft around them now and studying them, finding out what they're made of. They go all the way up. Here's Vesta again, this guy, and here's the dwarf planet Ceres. And not a lot of people today know about Ceres. Ceres is the lord of the asteroid belt. And a lot of people know about the controversy over Pluto, right? So Pluto, we all learned Pluto was a planet. And then it wasn't a planet, and everyone got upset. And then they're like, well, okay, it's kind of a planet. It's a dwarf planet. And there's all this, justice for Pluto, remember Pluto kind of stuff. But nobody remembers Ceres. And there's the same thing happened to this guy. So Ceres was discovered. It's large enough to become round. And I'll talk about, there's a little, that means something. When the early astronomers found a pattern in the distance between the planets, they saw, Mercury, Venus, Earth, Mars, blank, Jupiter. So in the 1800s, they started really looking for a missing planet in there. And then they found it, Ceres. And they named it, and it was in all the books, and it had a symbol. And then I'm sure there was some silly limerick that put a C in there, until telescopes got better. And then astronomers started finding another one at the same orbit, and another one, and another one, and another one, and all of a sudden they realized that Ceres is one object amongst many. And that's when it got demoted from a planet to just the biggest asteroid. Well, there's this very similar story with Pluto, right? First it was Pluto, then there was another one, and another one, and another one, and all of a sudden now Pluto's, the legacy lord of the Kuiper Belt. But anyway, there's an interesting story here. So in a way, Pluto's demotion was justice for Ceres because Ceres got elevated again to a dwarf planet from way back. So anyway, it's my asteroid bias, but there it is. So when you have an asteroid that starts out, you have little bits of stuff floating around in space. Gravity pulls them together. Eventually they collect, and imagine that the gravity is squishing those original bits so hard that finally you get enough where the center starts to melt. And that's the key. That's called differentiation. Then you start melting the whole thing, and it becomes a sphere, like a teardrop as it falls. Or you see pictures of astronauts trying to drink orange juice. They all make, surface tension spheres. When you differentiate a world, it becomes round, and you get a core in the middle and a crust on the outside. And there are different variations on a theme, but that is the differentiation process. That's how you make a world. Okay, Ben, why are you rambling about this? I thought this was asteroids, not worlds. Aha, well, there are 4 types of asteroids, as it turns out, which relates to the kinds of meteorites that we find. There's stony guys, silicates basically, stony iron, which is silicates with iron in it, ones that are just iron-ish, and then raw. And, well, as it turns out, there's a pattern to where these asteroids and meteorites come from. The stony asteroid, guess what? That's a differentiated crust. That's a little bit of crust of an ancient world that no longer exists, that was blasted off, floating around through space, and is either still there or it landed here as a kind of meteorite that we can attach to that kind of asteroid. And you can get basalts, things we'd recognize as like lava flows, original igneous rock. Great. Well then, the stony irons, guess what? As you move into the world from the crust just like ours toward the molten core, well, there's an intermediate spot in the mantle where you get some of the silicate stuff and some metals. And here's a slice, and now you can see silicates with metals. And the third type, iron asteroids, guess what? They're chunks of an ancient heart of a planet, an old core of a world that's long dead. But we've got these fragments. And you may see these in jewelry shops and rock shops. These sliced meteorites, this is a Gibeon meteorite, with these crosshatch patterns. They're called Widmanstätten patterns. And these are astonishing because, not to dive into the details, humanity cannot make this. And I think so there's nickel iron here, making 2 minerals, called camosite and taenite into an alloy. We can't make that. That's why in the ancient world, when people found magic metal from the sky and forged it into a sword, it would go through bronze like butter. It really acted like the Excalibur, stuff may be based on meteorites, because in order for these won't grow together as an alloy unless you cool them down something nuts like a degree per million years. We literally can't do it. If you do it any faster than that, they don't combine. So every time you go, it's cosmic. Like this is an alien material, right? That we can't make here on Earth. That's why whenever you see, like the ancient alien stuff, and they say, well, we might have found a metal that, we don't know. Every single geologist studying meteorites goes, oh, so you found a meteorite? We get space material that we can't make falling onto Earth all the time. So what do we have? We have bits of the crust, bits between, asteroids that are made out of bits of the core, and then stuff that never differentiated in the first place. They call them chondrites. It's little, if you slice them up, you see they're little tiny spheres that just clump together in space and nothing else ever happened. So this is what asteroids are. It's either perfectly original bits of our solar system, or they're blasted off chunks of old worlds that don't exist anymore. And I want to tell you something interesting. I'm into this stuff, obviously, but when I didn't know until I started doing graduate work that the science is so much farther than you think it would be. Every time we take a look at this, there's a way to, each one of these has a fingerprint. And you can tell whether it's similar or different. So you can start to say, did these meteorites come from this world? And scientists have been doing that for decades now. The minimum number of worlds that used to be in this solar system, by worlds I mean go through this process of differentiation and becoming a sphere and having a crust and a core, 80. That's the minimum number. That's just based on meteorites that we found here. Like what does that mean about the early solar system? It was very different than where we are now. So there's an excitement in just learning what asteroids are. So granted, that's asteroids. And now, where are they? Okay, we know what they are. Where are they? Well, most of them, here's the solar system, sort of cartoon. This is not to scale. But you've got, Mercury, Venus, Earth, Mars, and then Jupiter out here. Most of the asteroids are in the main belt, this guy here. It's about 5% of the mass of the Earth's moon, if you lump them all together. So on the one hand, yeah, there are a lot of them out there. But on the other hand, it's not as much as I think it's not like Empire Strikes Back, where the things are crashing into each other and there's like 14 feet between asteroids in space. I mean, these things are separated by tens or hundreds of miles, but at this scale, they look bunched up. But that equates to still a decent number, like 3,600 billion kilograms of material out there. And the ones we're worried about are called near-Earth asteroids. And what does that mean? That means it's not as many as the total, but there are quite a few of these, and this is a plot. Each one of these faint blue lines is an asteroid orbit that's coming in and out past where the Earth will be. Now, you have to have a magic strike, extremely lucky dice roll to get those two things moving that fast, an asteroid and the Earth, to hit each other. But there's a chance for a lot of these guys. So what are we talking about when we're talking about asteroids? We're talking about the near-Earth asteroids, and those are the ones that potentially threaten us. Now, I'll talk about this later, but NASA has been looking into this for quite some time, and this was just published, I think, 2 weeks ago. And forgive me for putting a giant, incomprehensible chart up here. I mean, I know that this is like, oh, here goes the scientist. But if you look at this, all this is showing you is down here is the super small asteroids. I think it's, 10 meters? So 30 feet all the way up to 20 kilometers. So you got feet scale to miles in size. The red line is how many of them we're pretty sure there are. So this makes sense. There are lots of very small asteroids, 10 or 100 million, really small things, and then nothing we're really sure that we don't know about larger than 10 kilometers in size. So in a sense, if you need something this big to just take out the dinosaurs, there's good news here. It means that we know, and this blue line shows how many of the asteroids out there we have tracked, we've located. So you can see we're not seeing just barely any of the little stuff. But the bigger they get, the more we've already found. So we don't have to really be scared of an Earth killer just showing up out of nowhere. The odds of that are exceedingly low. However, Tunguska, well, we've only found, 5% of the guys that are big enough. It didn't have to be that big to cause a huge blast. These things are moving quickly. So this is where we are, literally as of this month, 2018, in our asteroid search. So hence, we've got some work to do. We want to bring this blue line all the way up there so that we are sure we know something won't hit us unexpectedly within our, practical lifetimes. So why worry? Okay, I showed you that chart, which is kind of a prelude, but there's lots of stuff that hits the Earth from space. There's an exchange of material. I went and crunched the numbers. It's 100 tons of meteorites and meteoritic dust per day, which that's a pretty abstract number. But if you break it down into Volkswagen Beetles, that's about 7 raining in space per hour. So 7 Volkswagen Beetles per hour. Then you can wrap your head around that. It's spread out across the world, but okay, there's a fair amount of stuff that the Earth is collecting as it swings around the sun. And, okay, well, this is small stuff. It's pretty. It burns up. You might even see it, but it's not threatening. It's not going to hit the ground. But, like I showed you on that chart, there are more things, fewer than the dust, but more things that can actually do us harm. Why worry? Well, look at the moon. Let's take a really good look at the moon. Just kind of gaze upon it. We got really nice pictures of the moon now. And even if you zoom in, the farther you go, you see that each crater is cut by craters, is filled itself with little craters, which it's almost like you can't tell it is fractal, so you can't actually tell how far away you are. That's a lot of stuff. And we're right next to the moon, so we're bigger, so the odds that it took all, the stuff hit us too, but we just have erosion, water and wind that cover up the evidence, and an atmosphere that actually takes the brunt of a lot of this stuff. So here's the one that everyone knows about. In the late 20th century, the idea was finally popularized that big stuff can hit us. This is new scientifically, thinking that this is a real issue that needs to be addressed. And it's the Chicxulub impact crater that is off the Yucatan. It's about 100-mile diameter. It's associated with the death of the dinosaurs. Whether or not there were other things happening at the same time, there's some debates in the details. But yeah, we know there was a giant impact, and it definitely helped really hasten the dinosaurs' demise. So we know that happened. But hey, it was 65 million years ago. So really, do we need a whole international day for that too? Okay, hold on. I'll address the skeptics. One rule of thumb, you can take the diameter of a crater, divide it by 4, and that's roughly the size of the thing that caused it. It's not perfect, but it gives you something to start with. So that means an asteroid will create a crater 25 times larger than it is. Okay. Let's keep going. How did we find it, by the way? It's buried. You can't swim around in the Yucatan and see the crater in the bottom of the sea. It was too long ago. So if you do geophysics, that's where you can start to see the actual position of the crater, and this will be relevant for the impact that we're going to talk about. Then few people know Chesapeake Bay. That's an impact crater. And we found that via geophysics. It's about 56 miles wide. But it's still 35 million years ago. Do we have to worry? And again, we found it with geophysics, mostly buried evidence. But then, okay, meteor crater. This one's a lot more recent. Tens of thousands of years ago, not millions. 160 feet wide. The crater's 3/4 of a mile wide. So the asteroid shakes out to about 160 feet in size. Okay. Well, we're getting closer, but still, 30,000 years. That's, the house isn't looking pretty good here. I'm still going to play those odds. But we do have large new things. So that's what I talked about earlier, the Tunguska blast, 1908. Now we're in this century. Now we're talking megaton blast, things that don't have to be huge, but level, millions of trees and a town if it had been there. And then this is the stuff that really made astronomers nervous, but it never got any press. And this is what tuned me in. There was a comet called Shoemaker-Levy 9, and you can think of comets like icy asteroids. It hit Jupiter, this comet. So this is actually a picture of Jupiter in infrared, in heat. And this comet was ripped apart by Jupiter's gravity, and then like a shotgun blast, little bits of this comet went bang, 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 and made huge explosions in the southern hemisphere of Jupiter. Each explosion was larger than the Earth. And you can find pictures. This is 94. And that's when astronomers went, whoa, you see all that? And then they tuned Hubble telescope. They missed the actual explosions because they're too fast. But they saw the scars. And that's the actual size of Earth. They left a scar wider than Asia. So yeah, that's when the hair on all the astronomers' backs of their necks stood up and they're like, whoa, we just watched this happen. Like if that had been Earth, it would just totally destroyed. Okay. Well, and as it turns out, I don't think I mentioned it, but it happened again in 2003. We saw another scar hit Jupiter. They're like, whoa, this is happening a lot more often than we thought it might. But then we zoom in. Okay, that might have been an Earth killer with an explosion of that size. There are smaller things, but they're big enough. This is what put Asteroid Day on the map. 4 years ago, there was a bolide. There are lots of names for different, when it's out there, it's an asteroid or a meteoroid. When it's moving through the air, it's a meteor. If it burns up, it's a bolide. And if part of it hits the ground, it's a meteorite. So as if we couldn't make it more unwieldy, it's got like 17 names just based. It's like if you name like one side of the stage, I'm Bob over here, remember I'm Steve over here, and now I'm John when I reach over here. Anyway, I sympathize. So in February 2013, this meteor came in, and it exploded, which was bolide at that point, with an intensity 40 times brighter than the sun. Now, that's, and it left this huge contrail. It's dusk. The sun's already behind the limb of the Earth. But this is highlighted, so it looked weird. Everyone ran outside. And that was part of the problem. And let me dive out of this for a second, because it look good as a PowerPoint if you're not actually going to show some video. So here's a dash cam. It's going to loop. But this is the actual bolide coming in the distance, blowing up in the sky. So that's what we're talking about. It's a super shooting star. And you think, okay, well, Ben, that's also very pretty, but do we need to worry about it? And the answer is yes. And in the YouTube era, this is literally one of the most amazing videos I've ever seen. So what you're looking at is another dash cam, much closer, and you can see that it explodes with an intensity 40 times greater than the sun. Look at the sky. It's dusk. That's sunset over there. And here we go. No sound, of course, because it's too far away. Tens of miles, but it's coming in. This is not doctored. And when it blows, boom. And you can see it trailing off here to the right. And that would become a meteorite when it crashes. Now, the important thing is it left this big streak, right? So everyone saw the flash. They ran outside, completely unaware that there's a shock coming, and it's invisible, just like a meat blast. So right about... That's the sound of every window in the Russian town of 40 Minsk blowing at once. And the car alarms, every car in the town blowing at once. I mean, let's just, I'll stop talking and let you guys actually listen to that. I mean, this is like a Michael Bay moment in real life. Like this almost, and it's on film. You never get to see this sort of stuff. I mean, very calm. And so now, if you guys were in the Atomic Testing Museum, if you've seen the videos of, an event, and there goes the mushroom cloud, and you see that wave disturbing dirt as it comes up, that's what's coming down from the sky. And everyone ran outside. So what you see up there also is basically the stretched out version of a mushroom cloud in the sky. Right here, you can see the mushroom cloud forming. That's where the largest part of the explosion was, and it starts to draw air in and go up. So from there, it blew up. I'm getting the altitude wrong, but I think it's about 10 miles. What did it do? Well, it damaged 7,000 buildings and injured 1,500 people. So it was at that moment in 2013 when the world took notice. this was an event. So yeah, the asteroid was only 60 feet or so in diameter. To do that kind of damage, megaton, many megaton grade. And it's important here that, when you see a flash that's brighter than the sun, just like a nuke blast, even if nature causes it, that was the lightning and the thunder's coming. So it's something, and this is exactly the sort of awareness that Asteroid Day is trying to build. So I know I'm belaboring this, but I wanted to get to that video because that's really, there's the point of explosion. There's that, you can think lateral mushroom cloud. Physics is physics. So it's not radioactive, of course. That's what makes a nuke different than this. But an asteroid is actually, an impact is the only thing nature can make that gets as hot as a nuke. We'll start to see. Here, this is another. This was published again just a couple weeks ago. It's a map of every asteroid, tiny asteroid explosion in the sky we've measured from 1994 to 2013. The blue ones happen at night. The yellow ones happen during the day. So this is not hypothetical. It happens. Were people injured with these? No. Chelyabinsk is right here. It's the biggest one on the map, but not by much. So, okay. I think you can justify. There are a lot of skeptics out there, which is fine. Do we really need to worry about this? Well, the more we look, the more it goes, well, yeah, I think there's a good justification for it. Now, is there anything closer to home? The answer is yes. This is what we get to. So discovery. In the early 1990s, geologists were wandering around, south central, east central Nevada and western Utah, and they found mysterious breccias, which is the name for a shattered rock. Think of it as a conglomerate, but everything's sharp. So something happened violently, quickly. Earthquakes will cause that. Near the town of Alamo, Nevada. Became known as the Alamo Breccia. So what are we talking about? Here's Nevada in topography. You see all the basin range, physiography here. There's Vegas, and the star is where Alamo is. And what does this breccia look like? Well, when you slice it in half and polish it, it's a collection of other jumbled up rocks, which have been highly fractured. Okay. Well, these rocks are ancient, and we're talking, five times older than the one that the potential impact that took out the dinosaurs. Not 65 million years, 380 million years ago. Maybe you can think 400. Well, there's a problem there. If you're trying to reconstruct a story about something that old, there's not that much evidence left. So, they're buried deepest because they're oldest, so some giant earthquake or process has to bring them back up so we can actually study something. They've been jumbled by earthquakes and faults and eruptions that happen and may have destroyed all of it, with time. So there's a data problem. It's kind of, one way I like to think about it is an archaeologist studying parchment. The original scroll is gone, but you find a few fragments with a few letters and words, and you try and reconstruct what the scroll originally said. This is kind of the geologist version. But one thing to understand what it is we're looking at for something that old, well, you got to realize that Earth had many forms, and most of those are sort of alien to the way we view the world today. And what I mean by that is, if you understand what we find now, you got to understand what was happening then. So you have to become kind of a time traveler here, which is what I think is pretty cool about the geosciences. So we found these shattered rocks from 400 million years ago. What could they possibly mean? Well, the Earth then, based on all the data we've collected for a century, it didn't look like this at all. It looked like this. And there's one guy, one expert, his name is Ron Blakey, who does the painstaking work of surveying the entire world's geology papers at one period in time and stitches together where every coastline was, where every deep water, where every mountain range, and he makes the best maps we have. And they change as continents migrate, as things occur, new mountain ranges are built. He has maps for every basic time period, which is sort of amazing. So look at, it's not quite Pangea. That hasn't happened yet. There are actually cycles of that. Supercontinents, and then they break apart. And they make a new supercontinent, and then they break apart. So here we are. And where specifically are we? Where's Nevada on this? It's, it's not up there. Where we were, and I should say, there may be some out there. How do we know that? Okay, Ben, full stop. Wait, 400 million years ago, guys drawing coastlines, like, come on, are we just making this stuff up? No, and if you want to know the 40,000 foot view, it's that when continents move, it's because seafloors are expanding, like the mid-Atlantic ridge. New crust is forming and it's shoving the other stuff to the side. What does that mean? Well, it makes these ridges, like the mid-Atlantic ridge. You got molten material coming up and spreading things out, which is shoving us away from Europe right now and shoving us toward Japan. It's about 1 millimeter a year. You can measure it. Well, we also know that the Earth's magnetic field has flipped over time. When this new rock comes up from the ocean floor, the direction of the Earth's magnetic field is frozen in it as soon as it freezes. So all the little iron molecules are all pointing in the same direction, north. And when it flips, all the new ones are pointing north. So what does it mean? It means as this spreads, you're going to end up with stripes of north-south, which are symmetric on either side of the ridge. And what that does is it basically, you can use this by combining those stripes back together as you get farther and farther. You know the spreading rate, you know where those alignments are, and you can start to reverse the process and bring continents back to where they were until they meet. And then a really interesting thing happened is, so we did those maps, and those stripes are all over the place. And when you put one set of them together, guess what? Another set was revealed. Like, oh, there's multiple layers of this, and so it gets fuzzier the farther back you go, but that's how scientists have, determined that, oh, we can actually place where things were in time that's long ago. So, like a jigsaw puzzle with multiple layers, we end up finding North America down here. So that would place Nevada right about there. And the western part of what we have, California, didn't exist yet. It actually wasn't built up by collisions between other continents and things. So there was actually like a Caribbean Sea. And it was beautiful and crystal water. You got the shallow, light-colored sand, it would have looked like a paradise. But the rocks also tell us something about what was here then, too. Not just where it was, but what was there. What was happening there? Plants were just beginning to populate the land. There's no land animals at all. And ocean life followed it kind of to the intertidal areas, but nothing was really walking around. And forests were new. Plants were wreaking havoc on the environment by creating a completely new carbon cycle. You start seeing forest fires for the very first time in the geologic record. It's a very dynamic time. And it really is an alien world. When you start to dig into these layers and get to know one period in time on Earth, as opposed to most geologists, you try and take a huge stab at the whole thing. Well, this is history. Well, find an expert in the Civil War. They really get to know that event in that period. You do that in geology, and you start wandering around an alien world. What today is mesas was an ancient coastline diving off into deep marine sea. You get these weird things. I'm not a biologist. Biology's magic to me. It's all sorcery. So I don't remember all the names of this stuff. But I can tell you a star explodes, but I have no idea how this critter, senses. I have no idea. How do plants turn sunlight into sugar? It's a different science. I know my limits. But anyway, you start to see what's happening here. These weird crawly guys. The surface is covered with plants that are primitive. They really don't look like ours. And when they mature a little bit, you get forests, but they're weird. There are no flowers yet. That hasn't even shown up. So it's an ocean world. And plants have just colonized the land. So that paints the scene. And when I say it's an ocean world, there were some pretty horrifying apex predators floating around in those seas, dominating them. They didn't survive an extinction long before the dinosaurs, but after this, they disappear. And one I want to point out, the lord of the ancient Devonian Sea was the Dunkleosteus here. This is a fish. This is the silhouette of a human, just to give you scale. It's like a school bus, right? This is all exterior bone. So this is an armored fish. This like a swimming jaws of life or something, but jaws of death, I suppose, literally. It gets crushed through things, and the teeth came straight from the bone. Very different world. So, okay, great. Now that we know what's going on, what about this breccia? Where is this all going? Here we are. That's Alamo, Nevada, way back then, 400 million years ago. If you tilt everything, this is a ghostly outline. I know you guys in the back might not be able to see it, but this is the Midwest. You can see Great Lakes are over here. Here's Colorado, Utah, and Nevada. It's kind of doesn't really exist yet. I mean, and this is not down to the foot or anything. So there's a lot of play here. But right out there is Alamo, and you can just see some of the eastern shallows. So the Alamo breccia indicated something enormous, something violent, but what was it? In the mid to late 2000s, we started to find key fingerprints that are only found where you have an asteroid impact or a nuke. And unless the superfish were lobbing nukes at each other in the late Devonian, well, you pretty much are concluding some kind of massive cosmic event. So what do we find? Shock quartz. Basically, you have a blast, and it recrystallizes the quartz. It goes like, and tells you which way the explosion came from. There are fire bombs called lapilli that result from, we see them a lot around volcanoes. In the movies, the flaming rock from the sky that hits the ground and explodes, that's a lapilli. Tsunami deposits, believe it or not, they found one on the east side of Frenchman Mountain. It's the right age. So they actually have the evidence of a tsunami created by the Alamo impact right over here on the top of a mountain. We're starting to stitch together a story, people. And then iridium anomalies. A lot of time, this is one of the things that nailed the Chicxulub impact that's related to the dinosaurs. Basically, there are elements that are rare on the surface crust of a planet like ours, but they're pretty common in certain types of asteroids. So if you find it in a concentration that's unusual, an anomaly, well, that tells you that something contributed to the surface. And so all these things we started to find in these few shattered rock layers outside of Alamo, Nevada. So these lapilli, basically, if you look at them sliced open, this is what a firebomb looks like that's 400 million years old. It's got a core that crystallizes, and you start to see this rim and crust. So that's one example. And then over the last 10 years, I mean, this is a geology diagram, but all you're looking at is if you stared at the face of a rock and started to piece out what type of rock is it as you look up and down the mountain. This is a diagram that tells you, and they start to anchor it. You find specific fossils that tell you this time. You do a radiometric dating that gives you a certain time here, and you start to explain it. As it turns out, the Alamo breccia came in 4 layers. And they each tell a story. And I don't have to dive that deep into it, but basically there's rock that melts when an asteroid smashes, and it kind of squirts molten rock down. There's the first stuff, the huge bits that are broken off and fill in the crater. Then there are, as waves of tsunami come and fill things, spread things out over the land and then scrape it all back in, fills in. There are certain patterns you can expect, and we find them. So here's the subtypes. 3 and 4, you got the big jumbled stuff on the bottom, basically, and it gets less and less chaotic as you get toward the top. So this is starting to make a very clear story. Now, full disclosure, the entire scientific community has not swallowed the Alamo impact. And is it because any of this data is bad? No. But as I'll show you, it's not necessarily complete. So you'd have a hard time coming up with other explanations for the things you find here, but we're still in the process of building the mountain of data that you need to prove something really big. And I don't think you'll see, it's not hard to see why when you see what this suggests. So there's one hypothesis that fits the evidence, and that's where, you smash out a crater, you got a huge water spout and tsunami, and you start boiling up rock types, and then you end up producing what we see. Conclusion? Extraterrestrial impact. Now it's just selling the rest of the world on it. But people who get into this, I'm a pretty skeptical guy, and I'm sold. But you'll see what we need to do yet to bring it home. So how big was it? Okay, let's get to the punchline. All right, we got Nevada's own impact crater. All right, great. This is this cosmic stuff. Well, we got to find it. So here we've kind of zoomed in on the county level. Here's Clark County down here. Vegas would be down there. Here's Caliente, Hyco, Alamo, if you guys have driven up north that direction. And let me see. There are only a few spots. So every one of these circles is one of the only spots where the right age of rock we can even get to. It's not like 2,000 feet underground or lost to the sands of time because it was brought up to the earth 10,000 years ago and rain destroyed the whole thing. So when you start, in the 2000s, they tried to find the rim, right? If this was an impact crater, there'd be a rim, a circular shape. And when they started doing that, early estimates suggested the minimum amount of material that it let go, 70 cubic miles. So hence a lot of the initial skepticism. You know, people were like, wait, whoa, you're not talking about a little, this is a huge event. For context, I just, to paint the picture, the largest crater we've been able to make on Earth is Sedan Crater out at the Nevada National Security Site, the test site. Its displacement was, 0.001 cubic miles. It's 100 kilotons. So if you start to weigh the relative size, well, I slightly exaggerated, this is Sedan Crater. I don't know if you can see this minuscule little dot. And what the data suggests from up to 2015, looked like this. Here's Vegas. All these red dots start to tell us what the rim looks like. And you'll also see that all the research stops at the Nye County line. Anyone want to venture a guess about why nobody can get past the Nye County line? Okay, so now you can also see why scientists are having a hard time completing the picture, is nobody can get over here to do some measurements, and we'll talk about that in a little bit. But yes, so the current estimate, you imagine the Sedan dot you can't even see. This was Alamo. I'm generalizing, there are details like, it was stretched out maybe over time, but yeah, 100 miles. So this is equivalent to a dinosaur killer. Now, it's important that we don't see a mass extinction in the geologic record after this. So you go, oh, maybe that's a mark against. But remember I told you, there were no land animals then. Everything was swimming around in the sea. So there's much less potential impact to sea life. Sea life can withstand a whole lot of stuff. Basically, there's an asteroid impact over there, they just swim on over here. I mean, there's no tsunami undersea, to destroy things. They're very insulated. So that, because there is an extinction, but it doesn't happen until several million years later. So it couldn't have been attached to this. So, okay, fine. Let's say it did happen. Well, we actually have the tools now to tell you what it would have looked like. Not to get morbid, but what would have happened in Vegas if the Alamo impact happened today? What would that look like? So how big was the asteroid? How big was the explosion? If we just ran that, we have equations for all these things, based in part on a lot of the work done at the test site and also modern research and NASA stuff, things like that. So that handy rule of thumb. An impacting object 25 times smaller than the diameter crater it creates. That means we got a 4-mile wide asteroid. Now, we got most of those. You guys remember that chart where, we're down to about 100% identified that big. But, maybe 1 or 2 left. Certainly like the things that hit Jupiter. So for a 4-mile diameter asteroid, considering Vegas about 150 miles from the epicenter, which we think is near Rachel, Nevada. Again, we can't really get all the way there. We'll say it was an iron asteroid traveling at, devil in the details. It comes in, average water depth 30 feet. It's beautiful. It's a calm day, 80-something degrees in the South Tropics of the Devonian Earth. And if you're standing here, 6 seconds after the impact, you get a maximum fireball. That fireball is 100 times larger in size than the sun in the sky from here, and it's 900 times brighter. Now, you remember how bright 40 times was when Chelyabinsk exploded. So this is so bright, there's so much light, and this kind of radiation is not harmful like when we say radiation safety. Radiation, this is general radiation. There's so much, imagine a light bulb so bright, it immediately lights grass, trees, and clothing on fire. It's just that much, it just gets hot. Poof. And there's a flash. You see some of that in the nuke footage of like paint on the surface of cars, the structural effects test, surface of buildings immediately start burning. Like that, just the worst version you can imagine. And that's 6 seconds. So bang, 150 miles away. 6 seconds later, this huge super nightmare sun comes out in the sky and everyone dives behind something because suddenly everything that's bright is hot. 50 seconds later, the seismic wave hits. It's almost a Mag 10. It's a 9.7. Humanity hasn't recorded anything like that. So basically, you destroy every building we've built. That doesn't mean necessarily shake it down to rubble, but it does mean, the structural integrity is no longer trustworthy. 4 minutes, so that was 50 seconds, we're under a minute. So now, so what do you get? Everyone who didn't get just sort of immolated right there, everyone's putting themselves out, and then the huge earthquake hits, and they're like, you know, you crawling out of the rubble, and then you take a breath, like those guys after Chelyabinsk. They walk outside, and they look up and go, man, what was that just happened? Then the sky starts to get dark, because the ejecta, which has been traveling, you know, all the bits of rock, that 70 cubic miles of stuff, is sort of, anyone seen Rogue One, the Star Wars for a little bit ago? You know, in the Death Star, they do the test, like their own test site on a desert planet on a like galactic scale, and you see the ejecta come up. That was one of the few things I think that made all the geologists go, wow, I wonder if that would be what an asteroid that big size would look like. That's interesting. We've never modeled that before. So yeah, all this stuff starts landing. 4 minutes later, it's a hailstorm of rocks. Average size, a little larger than a golf ball out here. The heaviest stuff, the big blocks fall out way up back there because they're heavier. But no, we get, you know, fist-sized bits of whatever it was blasted up over there. And it dumps about 30 feet on us. So not a good day. So anyone who's now survived putting themselves out, survived the falling buildings, and climbs out of 30 feet of deposited ejecta, they have another, let's see how many minutes, yeah, they got another 8 minutes. So if they climb out in 8 minutes, they just breach the top, and then the shock wave hits. That thing that a lot of people, you should YouTube it, recorded at Chelyabinsk. It's supersonic. It hits at Mach 3, this shock wave, which means it's like 2,100 miles an hour. So it's probably carrying quite a lot of all that dirt with it, or those clods of fist-sized debris. The sound intensity is loud. It would hurt your ears, but this 150 miles away, no, it dampened it where it just kind of hurts your ears. I mean, that's the good news here, as opposed to, like, I don't know, rupturing your organs or something. And the bad news is anything that survived the Mag 9 earthquake and buried under, shrugs off 30 feet of rock hitting it, gets completely obliterated by a Mach 3 shockwave. And 90% of any trees that happen to be left on the mountain, the smoldering sticks that were standing there, those are knocked over Tunguska style. And then 7 hours later, the tsunami arrives. So if that wasn't bad enough, because remember then it was a coastline, so there's a chance for reflected basin tsunami. And I think this is actually modeled here. So that means from here, it caused an earthquake so bad in the Pacific that it caused a tsunami that was tall enough to come back and actually reach Vegas. And it's only 6 and 12 feet high by the time it gets all the way over here, so that's nice. So if you want proof of the wisdom of maybe thinking about something like asteroid protection, you don't have to go any farther than Alamo, Nevada, and that's the asteroid day. So great. So what does this thing look like, right? You can actually drive to this. Now I will warn you, it's not really exciting looking to anyone who is looking for something like a crater, unless you happen to be a working geologist. Even then, this might not be your thing. But what it means, I think, is very interesting. So I went and hunted for the breccia myself before I wanted to give a talk on this. I wanted to actually put my hands on it. I can read everyone's papers in the world, but I wanted to see it. I'm a curious type. So the Hyco Hills location. There's Alamo. This is one of the first spots they found. The Geological Society of America, they've got a field guide diagram, and here is the front side of the mountain. Now it just looks like, I know, I used to not be a geologist, so I could go, wow, it just looks like a thing. But what you'll notice, and this is a sort of a geological diagram of this. So, this is a decoder ring for this. You got all these nice lateral lines, and that's a calm, deep water, normal muds just layering slowly over time and building up continental shelf rock. Okay. And down here is the same thing, but you notice it looks a little messy in here. Well, what everyone drove right by, right when the road splits, as you drive north past Alamo, you can turn right to go to Caliente, you can turn left to go to Rachel. If you turn right about 1 mile and look out your window, you see that mountain right there. And all these ruptured chunks, geologists drove by and realized this is like 300-foot wide sections of rock that were busted off and then frozen in place as a giant. They call it a mega breccia. It was so big, nobody saw it. Because if you're down here looking for small things, it looks like it all connects, but they had to kind of step way back and go, oh, whoa, there's like a floating piece right here that's 50 feet wide, and this is broken off, and that. So this is what told the tale at the very beginning, in the early 90s. I think it was 93. So I went out there this a couple years ago, and roughly between my fingers, the best I could do, that's the breccia layer, and you'll see, compare the mountain peaks. That's, I was there. So now the trick is, getting to it. It's like 600 feet up there. So you start at the Heiko Hills, and almost immediately, the world starts telling you a story, right? These are the parchment bits that start showing up, and you start reading words and letters. And so you see here undulations. You've got flowing water that's flowing enough to create dunes, basically. And you could see things are calm. All right, this is the marine environment. So we're in a sea, okay. But sooner than I expected, you got breccia. So this is a rock hammer, and you see this, it literally looks like fractured rock. It's one of the best examples I've seen. These bits look like they were blasted off and then frozen into place. You get this kind of stuff from earthquakes sometimes, but it doesn't tend to look like this, and then it certainly doesn't go where it goes from here, which is what you're seeing now. I know from the back this will just look sort of gray, but you got large chunks here that are all different colors, fractured, and they get smaller and smaller and smaller. Well, what's happening is you're seeing time playing forward. The heavy stuff is settling into this crater, and then lighter and lighter stuff is filling in as the waters calm down and the tsunami, calms down, and the world tries to, regain a sense of normalcy. And then finally I get back to the target. So this is how far my truck is, right there, I think. I found that all geologists must think in the same rock, because the one spot, I just pick a spot on the mountain, right? You throw a dart. I just happened to walk up, and right where I went to collect samples, I find all these really conspicuous holes, which are sample drill holes, which must have been from the other research teams that came in 2012 and 2014 to study the Alamo breccia. So, if I had any doubt I was in the right place, it was like, oh, here I thought I was going to find something new. But it was nice to see it, but at the same time I was like, man, you kind of want to be the first one to stand in that spot at least. I'm like, oh no, they've been all over this. But it was good, I was there. And it's hard to, pictures don't do it justice. The size of this deposit, even here, is huge. That's a geology hammer. I don't know if you guys can see it, it's in the shade. That's the breccia in this one spot. So the sense of scale, it's one thing to talk about it. It's another thing to actually walk out there and put your hand on the 30 feet of stuff, effectively, that I talked about falling here. Here it is. It actually happened. It's not academic anymore. I'm touching it. And it starts to play with your mind when you're like, wow, I'm reaching back 400 million years into an impact. It's cool. So where do we go from here? What does this mean? Well, I think there's potential for a future discovery at the Nevada National Security Site. And remember I mentioned, it's obvious to everybody in this crowd why exactly there is a dead stop on the research at the Nye County line. And that's obviously because there's restricted access. Department of Defense, Department of Energy, this is dreamland out there, they call it. 300 miles of uninterrupted, no civilians allowed playtime for pilots, tend to call it dreamland. Researchers can't get there, or it's prohibitive. There are other things they could be working on and not deal with the hassle. But if you were to extend their research, and now this is where I'm modifying other people's stuff, but the dotted line, okay, just take a rough stab. Well, here I plot the test site boundary. And then there are a few sprinklings of the right age, but two key ones. There's Mine Mountain, which is a feature out there. And then there's also the Calico Hills, which are just north of the old nuclear rocket development station. And if you look, the reason that these two sites are very interesting to me is that, well, of course, the whole site was studied geologically. We were blowing things up underground. We wanted to know what the seismic signatures were going to look like when a nuke goes off so we can find if the Russians were doing it, things like that. So there's good data out here. And you might say, okay, well, since they didn't declare giant space impact back then, that pretty much closes the book on your case, right? No, well, the geological world at that time, so the 60s, 70s, and 80s, was just getting used to the idea that Meteor Crater in Arizona was actually caused by a meteor. So there's ironic connective tissue. It's completely backwards from, I think, what you'd expect. When I mentioned earlier that there's a lot of similarity between an excavation crater from a nuclear explosion and an asteroid impact, you'd think that when we made the nuke blasts, someone went, wow, that looks just like craters on the moon or something. And that didn't happen at all. Instead, what happened is the USGS had an astrogeology section out here, which I'm quite envious that I wasn't around for, and it was headed up by Gene Shoemaker. You might remember that comet that smashed into Jupiter and with like several Earth-sized explosions was named Shoemaker. It was named after Gene Shoemaker, who was arguably the country's first real space geologist. And he ended up being one that would train a lot of the Apollo astronauts to walk on the moon. Well, our man Gene, who's very space-minded now, it's sort of like when I wander, people sort of pat me on the head and go, that's nice, Ben, like, let's get back to, but I'm like, guys, this is just like space stuff. So Gene's walking around there like that, and he's way by himself in the 60s, and the Teapot S shot, if you guys want to Google it sometime, this is one of our shallow, one of the events that made a crater. It wasn't that big, far smaller than Sedan. But Gene's walking around, and he looks at the side of this crater, and he goes, and at the time he was in the middle of a fight. He was the only one that thought Meteor Crater was a meteor. We now call it Meteor Crater. They didn't then. They thought it was a weird kind of volcanism. It's because they didn't find, basically meteorites in the center of the crater. They said, Gene, it's not. It's not, man. Let it go. And he's wandering around the test site, and he looks at Teapot S, and he suddenly sees that there's a pattern that as the rock layers are broken and folded over on the crater rim, that's exactly like what you'd expect if an asteroid came down and caused an explosion, and when you press play from that point forward, everything else goes the same. The blast comes out the same way, the physics works out the same way, the shock goes, the temperature is the same, and he had his guys bulldoze a swath right through the side of the crater so he could basically publish a paper that said, look, here's Teapot S's crater, and look, here's Meteor Crater's crater. A volcano won't do that. And so he actually used the site. He used nukes to prove that an asteroid crater was an asteroid crater. So the scientific community went that way. We had nukes first. It seems so it seems so obvious now, so much stuff, but it wasn't then. He had to fight that fight in the 60s. So here, in the 60s, the conventional geologists who were studying these areas, they didn't think about space stuff hitting us. They were just mud flows or earthquakes or things like that. So these reports, I picked these two spots because these breccias are there, and they're described. And they're just kind of waved off as, they're kind of weird. They may be too thin, or there's some anomalous stuff, but they're mud flow breccias, and then they moved on. So I think maybe now, with more modern eyes on it, there's the potential that these are misidentified breccia sites. And there could be basically extraterrestrial evidence just staring people in the face, waiting to get out there. But no one's been authorized to go yet. So that's potential discovery. I could talk about that all night, but I won't belabor it. So finally, could we stop one? Right? That's where this is going. What the asteroid did, it's great to see it. We can watch it all the way in, but that's not going to do us a whole lot of good. So NASA is aware, and they recently opened the Planetary Defense Coordination Office, which is where they're asking the question, what can we do about it? They tie in with FEMA and say, okay, can we prepare people in case we do think something is coming, if nothing else? And also, there's a newer idea, and one, I will say, the less exciting, there's a program called DART, where they're basically going to smash a small spaceship into a tiny asteroid and measure the difference in deflection and prove all their models. So take it off the whiteboard and then, put it into practical application land. So if we ever had to do that, it turns out if we had some lead time, all you have to do is build a heavy weight on top of a rocket and smack an asteroid real hard, and it'll just nudge it over, and that's enough if you're early enough. Anyone who's done any range shooting knows that the farther away from the target you are, the more accurate, the more the deflection makes a difference. So this is the same idea. You're extending the range to target and kind of nudging the nuzzle of the asteroid over so it misses the Earth. But if it's too late, if we don't have that much time, or if it's too big, if there is one of those big ones floating around, NASA partnered up with the National Nuclear Security Administration, and we have the Hypervelocity Asteroid Intercept Vehicle. And it's government, so what are we really talking about? Well, what they don't say, the word that is missing from this title, is there is a nuclear explosion device. Well, they're not going to go invent a new one. They're going to take something out of the stockpile and so they could just say, like, B-61 warhead, but they don't. It's the nuclear explosive device. So how does this work? It's a 1-2 punch. There's a leader spacecraft with sensors, basically the target side, and it's like 1-by-1 cover formation. And so the observer spacecraft goes in, and the nuclear explosive is behind. And the way it works, they realize, well, speed can be a weapon itself. None of these asteroids have a warhead in the front, but look what they do, right? It's all because they're coming in at 20 miles per second. That's really fast. And so you just take all that kinetic energy, boom, it's already a bomb. So if they just don't slow something down as it's approaching an asteroid, it's already a bomb. So meteor crater, just remember, no warhead required. So you go to this launch, and this is from a NASA, like a promotional video. Step 1, you launch it. It's about 1 kilogram per kiloton. So they can scale it. Okay. 300 kilotons or less. There's the Thor or Delta II rocket might be able to do it in Department of Defense land. Step 2, 24 hours before impact, those two things separate, your lead ship and your bomb. The leader gets ahead, and it's got a little impact sensor. It kind of strings forward. They're traveling at 45,000 miles per hour on intercept, and it's the only time we're not worried about hitting something. Step 3, so 23 hours and 59 minutes later, the leader comes in contact, its sensor hits the wall of the asteroid. And now we're zoomed into microseconds here. That arms the warhead. So, boom, that thing hits the asteroid, the warhead arms, that leader is going so fast, it creates a crater in the asteroid. And less than a second behind the leader, the follower enters the crater, blasted within the asteroid, and boom. They realize, based on the physics, that you can do way more damage either moving or destroying an asteroid with a 1-2 punch using your speed. It suddenly dawned on everybody, wait, it's already effectively a warhead. Why don't we use it? So the follower detonates in the crater, and it either blasts the asteroids into fragments, or if it's big, it just supplies a very effective push. So hopefully, this HAIV causes the asteroid to just miss, or it turns this civilization ender into just a volley of really bad days, which is not great, but better than the loss of all human civilization and life on the surface of the Earth. So there you go. Parting thoughts. Thank you guys for hanging with me on this. It's the irony, right? I mean, that's ultimately what I hope you guys register in all of this. Well, the most heavily cratered spot on Earth is the Nevada National Security Site, Nevada Test Site, likely sits inside the bounds of an asteroid crater. I mean, that's like a cosmic joke. Nobody planned that. Who could have thought? I think that deserves a bit more play. And the NNSS is a potentially important site of future research for proving this. You can talk about things you can do on the science we can extract. We learned so much about cratering and cratering processes from the test that went on at the site that helped us understand the moon, asteroids, planetary geology, the solar system over. Well, now we can study not just modern craters, but one created 380 million years ago. And so I like to say, there's more irony. The tools that we might use to divert a big one under NASA's HAVE program are former weapons of mass destruction that we turn into weapons of mass salvation. How cool is that? I mean, that's another reason to make stockpile stewardship all the more relevant, right? I mean, if we're worried about the bombs working in case Putin goes nuts, well, it's the same reason we might want to make sure that the warhead works if we really want to push a big rock out of the way. So I like it. And so could you possibly call the Nevada National Security Site a Nevada Planetary Security Site? It's something to think about on multiple levels. But what about for the smaller ones, right? Is there anything we can do? And this is something I really want you guys to remember, because media gets it wrong all the time, and it makes anyone who studies this stuff totally nuts. Yes, you can do something. You can duck and cover. And about every 6 months, you'll find an article making ridiculously, prevalent circulation on social media and stuff that makes fun of this. Right? Most people think, oh, bend over and kiss, it's over. You're turned into atoms, like duck and cover is total nonsense. Well, not only does that overestimate the destructive power of nuclear bombs, I mean, if, heaven forbid, one does go off, there are going to be an awful lot of people surprised that they're not a cloud of atoms, that they actually will look around and survive it and then go, whoa, now what? I never thought about this. So there's a great story, and I wanted it to be my closer so you guys remember it, from Chelyabinsk in 2013. And it's so good that you'd think the universe scripted it. So in Chelyabinsk, the flash went off, and you guys saw how bright it was in the video. Completely overwhelms daytime, anything that we consider normal. There was an elementary teacher in Chelyabinsk who was older, and she remembered her USSR duck and cover training, because they were doing the same thing for civil defense as we were. And instead of running over to the window or running outside to take out her camera and take a picture, and this is a lot like, now there's enough knowledge about tsunami that if you ever see the water draw out to sea, you don't run over to look at all the flopping fish and see how weird it is because there's a giant wave coming. This is exactly the sort of awareness. If you ever see a flash that's brighter than the sun, that's the lightning, and imagine the size of the thunder, and it's coming, like right then, and you don't know how much time you have. So what she did is she remembered her training, and instead of doing what everyone else did, she said, kids, get under your desks, now. And she started helping all of them under the desks. And as she's getting the last kid under the desk, bam, the shockwave hits. All the windows are blown in by the blast wave. She almost gets her left arm severed off, and no kids were injured. Duck and cover saved them all in that room from a 15 megaton blast 10 or so miles away. So, it works. Not only does it work, you're going to save people. So every time I read an article that's like, look at how stupid everybody was in the 60s thinking they're scaring kids by making them get into the desk. I'm like, you are going to kill people, whether from a natural process or not. If you make people think this is silly, everyone's going to run out to get the best YouTube video. And everyone's going to get hit by a blast wave, but instead of like a just gust of air, this is a Mach 3 blast carrying stop signs and Volvos with it. So you don't want to be out there for that one. You want to be under your desk. So yes, you can duck and cover. If you ever see a blast brighter than the sun, get away from the windows, get under something. It's going to save a lot of people, but tell your friends. And yes, the greatest threat from the blast wave is the flying glass and debris. And there are so many pictures of, just look at all this stuff. Glass is sharp. It's not like the movies. Everyone charges through a plate glass window and it sprinkles into harmless little bits. If you ever see that happen in real life, it's like you just ran through a whole crowd of people holding swords. You're really sliced up. So these are sharp. People don't realize that till they see it firsthand. And that's it. Thank you guys very much, and thanks to the Atomic Testing Museum. And I think, how are we doing for time? Yeah, so we've got time for Q&A if anyone has any questions. Sure.
The stuff you were touching pictures of that, is that asteroid material, or is that Earth material that was...
Excellent question. So the question was, when I actually went up to the impact crater, or not the crater, but the debris, when I was touching it outside of Alamo, was that a part of the asteroid, or was it an actual part of the stuff that was blasted by the asteroid? The answer is it was blast ejecta. It wasn't the actual asteroid. That's one of the missing parts. So since we haven't been able to get all the way to ground zero, there probably is still some physical signature of the thing that came. There's a chance that it vaporized itself completely and it's distributed, won't really find it. But something that big, you might find something. We just haven't been able to get to the ground zero. So that's a great question. Yes, sir.
Yes. What about asteroids that might be coming in outside the solar system?
The question is, well, what about asteroids that might be coming from outside the solar system? You guys may have seen some press about our first discovery that's very recent, and it's got a name that I'm ashamed I don't remember. There were a lot of O's and M's in it. We do need to, the answer is they have much greater approach velocities, and they're from an angle that's hard to see. And so, yeah, that could be a surprise on our chart. We think we've got everything figured out, but that's just internally. So that would make this even more relevant. That's an excellent point. Thank you. Yes, sir. Oh, let me move over here. Yep.
Given the limitations on launch vehicles and yield per kilogram,
Yes.
what's the biggest asteroid we might be able to deflect, and how does that compare with what this one seems to be?
That's a spectacular question. There are too many unknowns for me to directly answer it, and I'll tell you what the unknowns are, which I think will at least give you. So asteroids can come as solid blocks of iron, or looser blocks of like volcanic rock, or they can be rubble piles. So we can't see the difference right now from here. We don't have the technology. So we're probably going to shoot high, no matter what. In case, if it's a rubble pile, you run the risk of it being able to just sort of liquefact, kind of absorb more than you were counting on, or, you know, it won't respond in the way that you need it to. And so, I mean, as far as the largest one that we could nudge, that also depends on how soon we find it. If we find it really early, we could knock out the largest thing on the chart if we had a couple years. If we have a few months, even if we hit it with everything we got, it might not change its trajectory enough to not hit us, because Earth's got a pretty heavy gravity field. So it's really just going to depend on the details of the scenario. So the question really is time. If we increase our time, we can deflect anything. If not, we could be in trouble.
But what's the limit of detection of something as distances?
Well, it depends on its orbit. So off the top end of the chart, when they say we found better than 90% of all the, you know, kilometer or better guys, that means we're seeing them many years out. So we've got those guys, the ones we know about. It's the little ones, the Chelyabinsk size, that are surprising us. So we're seeing lots of those, maybe a week or a few days before they zoom between the Earth and the Moon, like close approaches. So the good news is we're a lot more confident about the largest ones, so we have the most time. But the limit of detection, it's hard to say. I mean, it depends on where they are in their orbit. So we're seeing a lot as far out as we can. Sometimes we catch them in days, sometimes we catch them years or decades. It's just, at this point, a luck of how lucky are we? When do we happen to catch them in our sights? That's a great question. Sorry. Yep, excellent points. So the answer is you're absolutely correct. What it's made out of is key to how effective your diversion mechanism is going to be. And so there is a chance for radiation pressure to do a bit of a shove from a nuke without actually hitting it, but you really have to have your math right on what that's made out of, and you know that's a more gentle use of the nuke. It can be very effective, but no, there are a lot of unknowns. The best case is that we send a precursor spacecraft out to get up close and personal and actually characterize this thing, and then we smash it in the best way we know. So you're right, again, there would be a lot of unknowns. If we panicked and did this, we'd just be taking our best stab at the most likely, you're trying to save the world at that point. So we don't have time for, to open the contracted bids and all that stuff. Yeah, so it's critical on this lead and chase spacecraft idea that and I think that was the purpose, was a timing issue, that if you knew their speed, which we would know well, at the time that it made contact, you knew where surface was. And so if you're not, because the problem is you can't have it, if it actually hits the asteroid before it detonates, it won't detonate, it's going to be a pancake. So it has to blow up slightly before it hits, or else it won't detonate at all. It's just going to be squashed. Yeah, well, no, it's not automated. It's an international coalition of astronomers. Here, the NASA's Jet Propulsion Laboratory has a Center for Near-Earth Object Studies, and basically they get astronomers with telescope time to look at asteroids all the time. My graduate work was actually on helping untangle, because you're trying to see what it's made out of from here. So all we have is what light bounces off of it. So there's quite a bit of uncertainty, and there's some fake outs. So working on trying to see through the spectroscopy, how, it's non-unique. There are several different things that can give you the same answer down here. So NASA has active programs visiting Galileo went by some asteroids up close and personal. The Near spacecraft did. Japan's got Hayabusa 1 and 2. And so we're starting to actually have at least some samples to compare to our observations and strengthen that. But you're right, that's a weakness that, we can only know so much from hundreds of millions of miles away. Yeah.
You mentioned how far above that thing never hit the Earth, right?
Right, so yeah, I'm trying.
You mentioned how far above the ground that thing exploded?
So, it's hard to claim that because we don't have anything left. So there's a range of options. I think the lowest I'd seen that it could have blown up was still miles above the ground and still do the damage that it did. So, if it was a smaller one traveling faster, or if it was more consolidated, you know what I mean? Like there's a whole, not really. We can make a good stab at it, but it's starting to look like you're absolutely right. What the gentleman mentioned, for those who didn't hear it, is the Tunguska blast. There's no crater. And that was a real hang-up for a long time until we realized that more loosely consolidated or weaker rock types or ice, like a comet, would actually blow up just like, not unlike how Chelyabinsk caused ground damage from an airburst that didn't leave real, crater evidence on the ground. A huge scale of the same thing, 15 megatons, not at the ground. Thank you I didn't mention it. It's 15 megatons blowing up miles in the air and still cause that damage on the surface. No, thank you. Yes, sir.
With all the space,
Yeah, it's, so there are two sides to that coin. Space debris, space junk is a growing problem. And, like the space station has to start adjusting its orbit a little more frequently because there's a big, someone's leftover space glove that the Russians threw off or we did. Traveling at the speeds they end up traveling, you could really damage stuff. So, having said that, our satellites are still really spaced out. Like what doesn't tend to show up is realities like the space station orbits at hundreds of miles above the Earth. Our geosynchronous satellites are orbiting 35,000 miles away. Like I think there's this impression that all of our satellites kind of orbit at the same height, but they really don't. And 35,000 miles, that's what, 5 Earth distances or something? Yeah, those are really far away as opposed to the space station is basically closer to us than LA is. If you just point up, right. So there's a lot of open space still. So it's not, with all these little asteroids coming in and blowing up in the upper atmosphere, there is a snowball's chance that maybe one of those hits the space station coming in, but there's so much space, I think it's still more accurate to think of it like two guys standing at 50 yards firing buckshot into the same spot in the sky and thinking, are any of the beads going to hit each other? Probably not. Everything's fast and spreading out. But thank you. No, that's a great point. Yes? No, and you can imagine how nervous it might make other countries if the U.S. says, oh no, there's an asteroid coming. We really need to put this nuke in space. It would have to be an international effort just so we don't accidentally start World War III. So it doesn't have to be us. I think at the point that, because it's already international, you couldn't hide it. Astronomers rely on observations from all over the world to identify and verify, hey, we think we found something, can you guys take a look? That kind of exchange happens all the time across borders. So at that point, I think it would really be driven by who's got a rocket ready first, the Russians or the US, and that would probably drive whose nuke goes on top. But, hard to say. But it would really be restricted, I think, to either the U.S. or Russia, because we're the only two, maybe China, I don't know. Yeah, China. But who has the tools on the shelf ready to go, or as ready as they'd be? So, no, but you're right. There are going to be some, the people discovering the asteroid may be going, we need to launch this thing right now. And there may be a lot of defense pushback from all over the world. That could be a problem if it takes too long. So I think the real answer is we're talking about it globally. So this is not just internal because the asteroid community is already global. It would just be connecting the dots to the defense folks. Like our astronomers aren't talking to Russia's nuclear people for obvious reasons. We're only talking to our own nuke people. So yeah, it's worth serious thought. Oh, yeah. Yeah, it's hard to not, so yeah, the statement was, there's a very nice new telescope that we've been paying, American taxpayers have been paying on for many years, and for the last several years, we missed our deadline, we'll launch next year, we'll launch next year, we'll launch next year, we'll launch next year, well, 2 years, and so it just keeps happening, and it just happened again. Yes, I think it's very frustrating. With any big project like that, I mean, you can do larger things, then you could probably get, I don't know, Musk to donate enough money to make that. I mean, I don't think you can do it. But it comes with, the dark cloud underneath the silver lining is that there are giant gears that have to turn in the government procurement and certification system and things like that. And schedule slips seem to be getting more and more normal. So it would be a shame if we didn't have an asset like that in space that we could use to find something. So yes, am I frustrated? I guess, yeah, yes. Yes? Can asteroids become a polygon? You know, have you been watching that's a very interesting question. So up until about 3 days ago, I would have said, nah, probably not. But there's a spacecraft from Japan called Hayabusa 2, which is actually going to take a sample from an asteroid and bring it back here. Well, until we send a spacecraft there, we don't know what shape the asteroid really is, until we start taking pictures. And this asteroid looks like a diamond. It's like an off-kilter square. So imagine 2 pyramids, one on the top, one on the bottom. It looks like one of those more obscure dice. What's that, a D8? Yeah, yes. So it looks like, I know, I'm letting my geek flag fly there. But basically, if you Google right now, Hayabusa 2, you can get close. There's a picture that was just published like 3 days ago of a polygon-shaped asteroid. So we don't exactly know why that happened yet. It was probably because it got smashed in a strange way. But no, that's a great question. Literally, we're finding new discoveries all the time, and you just predicted one. So good job. Keep asking questions. That's awesome. Sure. Yeah, and again, we've got the problem of non-uniqueness, that there are several possible events that could have produced the same crater. So
That's why they thought it was around.
exactly. So that crater tended, it didn't just liquefy, it vaporized. So it's more like what's happening right at a nuke, and actually what the debris, the trinitite, even though it's not quite the same, from one of these ejection shots like Sedan or Schooner, asteroids also make that, and they're called tektites, and they make all the same shapes, and they make all the same, that's why I think there's a lot of connective tissue that's not being used between the asteroid folks and the nuke folks, even when it comes to like forensics of if troops have to rush in after a nuke blast and collect samples, what are they looking for? Well, it seems pretty weird until you talk to a planetary geologist. Oh, there are kinds called australites, and they're all over the Southeast Asian area and Australia, and they make all these shapes, and they're tiny versions. There's even one that's the exact same size as some of the fused glass out on the site. It's from Zamenshin Crater in Siberia again, and ergosites are the name of the little fused glass that is precisely like fallout, the spewed frozen material from a nuke blast, just without the radioactivity. It's the same temperature. And oh, no, thank you. No, that's a great question. So lunar crater, the question was, am I familiar with lunar crater in central Nevada? It was another Apollo training site. There's some cool shots of astronaut Edgar Mitchell and Alan Shepard doing training there. It's called lunar crater, but it is volcanic. I mean, that's the counterpoint to the meteor crater, Barringer crater in Arizona, is lunar crater. It's called lunar crater because, well, I mean, it looks very round. There's some details that are different, but you can drive to that, and it's not on restricted land. It's just to the west. And so if you ever want to stomp around and do your own moon training, where actual moonwalkers did, just Google lunar crater in Nevada, and you probably need a 4-wheel drive to get all the way there, but no, it's a really cool, they have atomic tourism. You could literally have moonwalker tourism, and it's right here in Nevada. So Oh, it's Easy Road. Okay, I mean, I've heard conflicting reports, but, okay, yeah. No, thank you. That's a great point. Yeah, go see it. This stuff is here. Okay, well, if that's it, thank you very much for your time. Thank you.